Hi, my name is Shamaz. In last lecture, we had this definition of an ideal of a set X. So let us recall what we had in last lecture. So let us suppose X is a subset of the affine space. So then the set I of X, which is the set of all polynomials in the polynomial ring x1 through xn such that the polynomial vanish at each point of x. So this set is called the ideal of x. So this is indeed an ideal because we have not proved yet this set is an ideal. So let us do a short lemma here. So Ix is an ideal in the polynomial ring x1 through xn for any subset x of the affine space an. So the proof is like this. So one is a formal proof, i.e. to prove this by definition. So clearly the zero polynomial is an ideal of x since uh, the zero polynomial vanishes at each point of x. So for if uh, f is in ix, then minus f is also I mean in ix. So let f is in ix, then f of p is 0 for all p in x. So this would imply that minus f of p is also 0 for all p in x. So hence the minus times f is also in ix. Also for f and g in ix, f plus g of p, this is f of p plus g of p, and this is 0 for all p in x. So this means this is closed into addition, and also for for the polynomial q in the polynomial ring x1 through xn, and f in the set ix, we have q f of a is, well, let us call this p. So this is q of p, f of p, and this is 0 since um, So this is 0 for all p in x. So this proves that x is an ideal in x. So hence Ix is an ideal in the polynomial ring x1 through xn. Now this is the formal way to prove this is an ideal. So there is an alternative way to prove this is an ideal for that. So alternatively, so let us consider uh, say this f of x k define the all k valued functions on x. So be the set of all k valued functions on x. Then this set is a ring with respect to the pointwise addition and multiplication of elements in this set. So then clearly this set f of xk is a ring under pointwise addition and pointwise multiplication. So one should verify this. Now we can define a ring homomorphism. I mean, then the map, say phi from the polynomial ring in n variables to this ring f of xk, which is given like this. So phi takes a polynomial f here to the polynomial function evaluated at x. So this is a well-defined map. This is not just a map, this is a ring homomorphism. So clearly this phi is a ring homomorphism. So one can note that the kernel of this ring homomorphism phi is nothing but I of x. So observe that kernel of p is actually the ideal of x. So which is therefore an ideal. So one can note here that the image of phi is the ring of all polynomial functions on V. So note that the image of phi is the ring of all polynomial functions. So this phi is actually here the evaluation map. I mean, phi takes f, the f evaluated at x. So all polynomial functions on V, and hence by first isomorphism theorem, so this image of phi is isomorphic to the quotient ring mod Ix. So now this quotient ring over here, this is actually a K algebra, and this K algebra is called an F1 algebra. Let us quickly recall here what do we mean by an A algebra. So let us suppose, so this is about A algebras, where A is a commutative ring infinity. So A algebra. So let us suppose A is our base ring. So A is the base ring, which is commutative. So this is a commutative ring with unity. So then an A algebra, so this is actually a ring, say B, with operations plus and dot. So this B is said to be A algebra if B is itself a ring. So this is commutative ring. And this B with same addition is an A module. This has to be an A module. I mean, we must have an external multiplication which is like this, from B cross A to A, given by, so B, sorry, I is A cross B to B. So it is like this. So we take A here and an element X here, so it goes to AX. So this is I mean the external multiplication. So these two multiplications has to be I mean they they should be compatible. I mean, if I take two elements in A, let us take A1, A2, and let us multiply these two elements in A. So this is the multiplication in the ring A, and let us take two elements in the ring B, say x1, x2. So here this is the multiplication in the ring B, and this is a scalar multiplication. So this must be equal to the scalar multiplication of I mean of a1 with x multiplied by the scalar multiplication of a2 with x2. Now this multiplication, this takes place in the ring B. So these two operations should be I mean I mean compatible. Now this is what we call an A algebra. So an A algebra is a ring B which is also an A module. So it has two structures, I mean the ring structure and the module structure. So now in short we can express all this data in one statement. I mean uh, so we can say an A algebra is a pair, say B and Phi, where B is a commutative ring, is a commutative ring, and phi from A to B is a ring homomorphism. So then we call this pair as A algebra. We call this B as an A algebra, and this phi is called the structure homomorphism. So given different homomorphism, we have different A algebra structures on B. So one should note here that different homomorphisms gives different A algebra structures on A. So for example, so if A is any ring, so A is any commutative ring, then the polynomial ring in n variables is an A algebra. Now, when this set is an A algebra, we must have a structure homomorphism, say phi from A to this polynomial ring. So, with structure homomorphism, phi, which is in this case the map I, let us call this the inclusion map. When an element A goes to A, this is the the structure homomorphism. So this pair so this is an A algebra. So this is an A algebra. So more generally, so if we take an ideal, say I inside the polynomial ring x1 through xn, so this is an ideal, then we have the following sequence here like this. So from A to the polynomial ring A x1 through xn, we have this map I, which is the inclusion map, and from this ring to the quotient ring, we have had a natural map. So this is x1 through xn mod I. So this is the map pi. So then this ring over here, this is an this is also an A algebra. So then A x1 through xn mod I, and the structure homomorphism here is pi composite with I. So this is an A algebra. So, one can note here. Uh, so one can note here this pair over here. This is an A algebra, K algebra, because the structure homomorphism here is, so this is the K algebra. Where the structure homomorphism is, and the pi composite with I, where I is mapped from K to this polynomial ring, and pi is the the natural map from the polynomial ring to the quotient ring. So one should note here that, so this is the remark, the pair k x1 through xn mod ideal of x, why the structural homomorphism is pi composed with I. So this is a K algebra, and this K algebra is called the affine algebra of X. So this and is called an affine algebra of X. So we have a short lemma here. I mean this, as we have seen the function z. Um, I mean if x1 is contained in x2, sorry, if ideal uh, I mean if ideal I1 is contained in I2, then we proved earlier that this zero function is decreasing. I mean this z function is decreasing. I mean this would imply z of I1 contains z of I2. So the function I behaves uh, similarly like the function z. I mean this function I is also decreasing function. So we have a short lemma here. So let x1 and x2 be two subsets in the affine space such that this x1 is inside x2, then the ideal of x1 contains, so then ideal of x1 contains ideal of x2. So this is actually straightforward. So let us suppose there is some polynomial in ideal of x2. That means, so then f vanishes at each point of x2. So then f vanishes at each point of x2, and since this x2 contains x1, in particular f vanishes at each point of x1. So since um, x2 contains x1, then f also vanishes at each point of x1. So this would imply, so this implies this f is in the ideal of x1. Hence, so we chose this f in I of x2, and we ended up at showing f is in I of x1. So hence uh, I of x1 contains I of x2. So this I is also a decreasing function. So one should uh, remark that if so if x1 and x2 are subsets in the affine space, and uh, say I1 and I2 are ideals in the polynomial ring, then mm, first is that I1 contained I2 implies 0 set of I1 contains 0 set of I2. This is what we put earlier, that is zero function is decreasing, and if x1 is contained in x2, this would imply the ideal of x1 contains ideal of x2. So this gives I mean the inclusion reverse maps between the algebraic sets in an and the ideals in the polynomial ring in n variables. So therefore we have the inclusion reversing maps. So one map is from the algebraic sets or just sets. So from subsets in the affine space and ideals in the polynomial ring in n variables. So from this set to this set we had the map I, which takes a subset in affine space to an ideal inside the polynomial ring, and from here to here we had the map Z, where we take an ideal inside the polynomial ring and we associate it is zero set in the affine space. So actually they are algebraic sets because so algebraic sets in the affine space. So now our motive is to understand to what extent these two maps are inverses of each other. So this is our main motive in this lecture. So we have a short lemma. So let X be any subset in the affine space and uh, S be a subset in the polynomial ring in n variables. And then we have first is zero set of the ideal of X is actually the closure of X, and second ideal of the zero set of S is, I mean actually it contains the radical of uh, ideal generated by S. So actually it is equality here, and that is the strong Hilbert Nullstellensatz. So for at this moment we just prove this inclusion here. So we have the proof here. So first we prove the first item. So for this let us pick any point P in X. So let P be any point in X. So then for all f in the ideal of X, f of P is 0 because f vanishes at each point of uh, I mean each polynomial in this ideal vanishes at each point of X. So this would imply so since this is true for all f in Ix, so this would imply this P is actually in the zero set of the this set, which is the ideal of X. So this proves that so hence X is contained inside the zero set of ideal of X. Uh, actually, mm, so if this is this X is an algebraic set in AN, that means it is closed set with respect to the Zariski topology. Then this inclusion here would have been the equality. I mean, we would have equality sign here if this X would have been the algebraic set. So now let F is any closed set, so be any closed set, be any closed uh, so be any closed set such that this F contains X. Then the zero set of um, ideal of X is contained in F as well. So this means that this zero set of I of X is the smallest closed set which contains X. So this implies that the zero set of ideal of X is the smallest closed set in the affine space containing X. This is closed because it is in the algebraic set. It is a zero set of some set, hence an algebraic set, and hence a closed set. Hmm. But one can see here the exclusion is also the smallest closed set in the affine space which contain X. So that means this zero set over here, this has to be equal to the exclusion. But exclusion is also the smallest closed set containing X. Hence, zero set of ideal of X is actually the closure of X. Now to prove second item, so let us, we have to prove the ideal of this zero set is actually the radical, contains the radical of the ideal of S. So let F is in the radical of the ideal generated by S. So this would imply that some power of F is in the ideal. So then F of R is in the ideal generated by S for some positive integer R. So if this is the case, then for all P into 0 of S, this polynomial f to the power R vanishes at P, or F vanishes at P, because if f power R vanishes at P, then F also vanishes at P. So this would imply, so hence this F belongs to the ideal of the this set over here, ideal of the 0 of S. So this gives the radical of S is contained in the 0 set of ideal of S. Sorry, ideal of the 0 set of S. Now we have a short consequence of this result here. So we have a corollary. So let this script A be the set of all algebraic sets in An. In the affine space, and suppose this fancy I be the set of all ideals in the polynomial ring in n variables, then the map I from the algebraic sets of the affine space to the set of all ideals in the polynomial ring is injective, and the map Z from the set of all ideals to the set of all algebraic sets is surjective. So this is a straightforward consequence of the previous result. So we have the proof. So we know any subset x of an, any subset x of an, I mean for any subset of, we know for any subset x of an, z of I of x is actually x closure. But if x is but if x is inside A, then x closure is x. Then x closure is x, because this would imply that x is an algebraic set, and hence a closure set with respect to the Zariski topology. So, and hence z of I of x will be equal to x. So, in other words, this would imply that the map Z composed with I will be the identity map on the fancy A. So that is the map Z composed with the map I is actually the identity map on fancy A. So this implies I is injective and Z is surjective. So now we conclude, so by proving that the function I is decreasing, I mean by proving if x1 is contained in x2, then ideal of x1 contains ideal of x2. So we conclude from this result here that the smaller the algebraic sets are, the bigger their associated ideals are. Now, since the points in the affine space are the smallest algebraic sets, so they should correspond to the maximal ideals, because these, I mean, the single point sets in the affine space are the smallest algebraic sets. So their associated ideals must be in some sense the largest ideals. So let us remark this here. So since the points in the affine space are the simplest and the smallest algebraic sets. So they should correspond to the maximum ideals. The maximum ideals. So if P is a point like this, A1 through AN in the space, in the affine space, AN, mm, then the singleton P is actually the zero set of the ideal J. For J to be the ideal generated by x1 minus a1 so on xn minus an in the polynomial ring kx1 through xn. So furthermore, this J being a maximal ideal, I mean this J is a maximal ideal because, so furthermore, J is a maximal ideal since the quotient ring is actually field, since the quotient ring, I mean k x1 through xn modulo the ideal J is isomorphic to k, so this J has to be maximum. Now the singletons, I mean the singletons P being the smallest algebraic sets, this would imply that the ideal J is contained in the ideal of this singleton P because this is the largest ideal because this P is the smallest algebraic set, but J is given to be the maximal ideal. So this would imply that these maximal ideals are of the form the ideal uh, of this singleton P, which is ideal of this P is zero set of the ideal J. I mean this J is same as I of Z of J. And the weak form of Hilbert's Nullstellensatz says that these are the only maximal ideals in K. So we do not prove the weak Hilbert Nullstellensatz. So we just state this here. So this is weak Hilbert Nullstellensatz. So the maximal ideals, the maximal ideals in the polynomial ring kx1 through xn are precisely and the ideals of the form I of ideal of the singleton P, which is ideal generated by x1 minus a1 through xn minus an for some point P equal a1 through an in the affine space. So this is the weak Hilbert Nullstellensatz. Now this is an immediate consequence of this result. Uh, so for every ideal I in the polynomial ring in n variables, the zero set is always non-empty. So for every ideal I inside the polynomial ring, the zero set of I is always non-empty. So this is a powerful result. This guarantees us that as long as this I is an ideal in the polynomial ring, it is zero set is always going to be non-empty. So one should note here K has to be algebraically closed, otherwise this is not true. So proof. So let I be an ideal in the polynomial ring. Then I is contained in some maximal ideal, because we know that every ideal is contained in some maximal ideal. So then I is contained in some maximal ideal in, say, maximal ideal, say M of the polynomial ring. So we know any non-zero ring R has a maximal ideal. So this would imply that, therefore the ring kx1 through x and mod I, this also has a maximal ideal. Now any maximal ideal of this ring must contain I. I mean, uh, an ideal of this ring correspond to an ideal in the polynomial ring kx1 through xn which contain I. So, but the weak Hilbert Nullstellensatz guarantees us that this M is of the form ideal of some singleton. So that is I is contained in M, but this M is equal to I of P for some, let us call this J, because here by I we mean the function. So let us call this J here. So let's call this J. So this M has to be of this form, where P is some point in, so for some point P in the affine space. So now, so now the function I being decreasing implies, sorry, the function Z being decreasing implies zero set of the ideal J contains the zero set of the ideal M, which is the ideal IP, and the zero set of this ideal P. Now this P being an algebraic set, so this Z composite with I is actually the identity map. So this is the singleton P. So that means J was chosen arbitrarily. So it is zero set is non-empty. So this implies the zero set of J is always non-empty. So one should note here that if K is not algebraically closed, then the above result is not true. For example, if k is equal to r and let us take j to be the ideal generated by the polynomial x squared plus 1, then the zero set of j is empty. So one should keep in mind that this k has to be algebraically closed, otherwise this would not make any sense.